A very good evening, everyone. It's my great pleasure to welcome you all to the fifth day of our ATAL Faculty Development Program. Over the past 4 days, we have witnessed insightful sessions, engaging discussions, and thought provoking ideas that have enriched our knowledge. Today, too, we have two sessions lined up, which I am sure will add immense value to our learning journey. Our first session for today is by Mr. Avinash Yedlapati, who will be sharing insights on AI tools in VLSI design. Dr. Dr. Avinash Yedlapati is a seasoned VLSI professional with 18 plus years of industry experience in design, verification, synthesis, and STA. He is currently a senior engineering manager at Altera Corporation Intel, specializing in low power design implementation. His career spans leading roles in global semiconductor companies, including Qualcomm, AMD, Synopsys, and Xind. Alongside the industry, he contributes to academia as a professor of practice at VNR VJIET and visiting faculty at BVRIT and UNIMAP, Malaysia. He has mentored and placed 200 plus students in core VLSI roles, bridging the gap between industry and academia. An IEEE senior member with a PhD in low power DFT, he is also deeply committed to education and social reforms through his trust initiatives. With great expertise in this area, Mr. Avinash sir will certainly provide us the practical insights and deep understanding. Let us welcome our speaker for this session.
Thank you, madam.
Thank you.
Let me know once you can see my screen, madam.
Yes, sir.
Can you see my screen? Can you see
sir.
Yes,
sir. Yes, sir.
Okay. So today I will be talking about the EDA technologies, the evolution, how VLSI has evolved on the EDA technologies in the AI era. So this session will be briefly about 45 minutes, and I will leave about half an hour for you people to ask any questions. So AI, I will not spend too much time on the introduction because all of you know what is AI. However, just for the sake of presentation, AI is basically the simulation of human intelligence processes by machine, especially computer systems. So we are in the AI era. Everyone, it's basically a buzzword for everyone. So how AI can help the VLSI technologies, in what way it is helping us. So that is what I'm going to talk today. So AI makes it possible for machines to learn from experience. We adjust to new inputs and perform human-like tasks. Now, all this, while all this is theoretically good, technically there are a lot more applications for AI in VLSI. So I will be going directly to the slide which actually talks about the VLSI stuff. So if you have any questions, you can ask me. Yeah. So this is the slide. So we have AI in VLSI design, and it is actually ramping up to a huge scale now. So we already have a lot of applications in VLSI design. So some of the applications are design exploration. So I will talk about each of these in the coming slides. Automatic test pattern generation, ATPG, which is part of DFT, design for testability. Then we have the RTL design automation. We have the physical design enhancement. Yes, madam. Hello. Yes, madam. Yes.
No, sir, you can carry on, sir. There is a noise from the participant side.
Sir, Avinash sir, I think your mic is muted. Hello.
Can you hear now?
Yes, sir.
Yes,
Yes,
sir.
sir.
Oh, sorry. Actually, okay. So, okay, then let me start from the beginning. So basically, so I was talking about AI in VLSI design, and we have huge number of applications in VLSI design uh, using AI. So some of the AI applications in VLSI are design exploration. This is in RTL and architecture level. Then we have automatic test pattern generation, ATPG, which is again a part of the DFT or design for testability. We have RTL design automation, where we can actually automate the complete RTL flow itself. We also have physical design enhancement like the PD, all the PD tasks like placement, routing. So there are so many things that we can automate using AI in the PD flow or the backend flow. We also have fast design exploration and innovation. Again, this is also related to the architecture. You can actually do a lot of architecture stuff using AI. Then we have predictive modeling and fault tolerance. This is again part of the DFT, the design for testability. And last but not the least, we have analog and digital circuit development. So all these are not complete list of the applications of AI, but there are due to the time constraint and due to the scope of the presentation, I have limited my presentation to only 7 of these points. So we will see each of these in detail, like how AI is actually making an impact in each of these areas. As you know, VLSI is a very vast area, and in this area we also have multiple domains like analog with digital domain, analog domain, then analog circuit domain, analog layout domain. In digital domain, again, you have the front end domain, you have the back end domain. So there's a huge application of AI in all these domains. But however, we will just focus on RTL and some PD and then DFT. So I am not going to go too much into analogs, but yes, I have kept a couple of slides for someone who is interested in how AI can help on the analog side. So I will go to the next slide. Can you hear me, madam?
Yes, sir.
Okay, so the design exploration in VLSI. So what is this design exploration? So we usually have a lot of genetic algorithms and evolutionary learning that can be used to optimize various aspects of the VLSI design. So there are a lot of algorithms in VLSI which typically we use MATLAB to actually test the algorithm, and then probably we take it into the actual chip design, into the VLSI design, and then we convert it into hardware, right? So, but now we also have AI, which can actually reduce a lot of these efforts. So previously, how it used to happen is manually we used to determine the critical paths. Let's say there's a new concept, or let's say there's a proof of concept that we need to deliver, okay, in hardware. So typically we get the algorithm, and then we test the algorithm in MATLAB, and then we actually try to write the Verilog code for that in HDL, and then we actually do a complete manual effort in reducing the power consumption, and also like determining all the critical paths. And also there's a lot of manual thing which happens when you actually take a proof of concept. But now AI actually helps us to determine the critical paths much before even the design is completely frozen. So how it does, we can actually see in the coming slides. Also, like, there are a lot of other techniques like frequency scaling and dynamic voltage, which are used to typically, like, if there is a circuit that doesn't work at a certain frequency, there is always something called as a frequency scaling, which we do to make sure that we let the design work at a much lower frequency. So let's say if a design has to work at 500 megahertz and it is not working at 500 megahertz, we do frequency scaling, and maybe like it works probably at 400 megahertz. And then also we reduce the voltage, or dynamically we change the voltage so that it can meet the timing or other things that probably manually it cannot meet. So all these techniques that we use manually now can be done using AI. So that is the first step, like design exploration in AI. Then we have ATPG. ATPG stands for automatic test pattern generation. So ATPG is typically a simulation type of work that we do in DFT. So design for testability is something like, design for testability is something like where we, I hope all of you have some background of what we do in design for testability. If not, I will quickly give a background of what we do in design for testability. So design for testability is typically a phase in VLSI design where we actually do the manufacturing. We actually try to catch the manufacturing defects in the chip. Okay, that is pre-silicon and also post-silicon. Now ATPG is kind of simulation, how we run simulations in front end. ATPG is also a similar methodology that we use to run simulations in DFT. So DFT means what? So DFT is typically to catch any like combinational circuit bugs or sequential circuit bugs we can catch during the pre-silicon debug. So we typically we remove the combinational or we remove the flip-flops, and we actually replace those flip-flops with scannable flip-flops, with our scan flip-flops, and then we stitch all the scan flip-flops, and then we run ATPG to make sure that all the bits are properly passing from the source to the sink. So how does AI help here? Okay, now it's a very tedious work for all of us to actually go and debug ATPG simulations, because there are so many changes in your scan chain, right? So you have like 1,000 flip-flops, then you have to monitor the behavior, the circuit behavior in simulations manually. But now, and it takes a lot of time, but now using AI and AI tools, now it has become very easy, because AI will do all the predictive analysis for you, and it will actually try to tell you that okay, this part of the chip probably has more bugs, or this part of the chips has more bugs. So it actually generates the test patterns for very complex designs automatically. So it will tell that okay, this particular pattern, so because we run thousands and thousands of patterns to find the bugs, but now because of AI will do a predictive analysis, and it will actually send very few patterns, but then because of those patterns you can still catch the bugs in the design. So if you see the fourth point, so AI can actually automate the generation of advanced test patterns for complex designs in the DV phase, in the design verification phase. So you save a lot of time. Typically, if you want to do ATPG on any chip, it will take like many days. But because of AI, you can actually reduce by almost 50% of your 50% of the time taken to debug all these complex designs. So that is the second application of AI in ATPG. Then we come to the RTL design optimization using AI. Now, RTL design optimization is one of the key things for any chip design, or one of the key challenges for any chip design. As you know, the design complexity is increasing, day by day, and there are so many. So previously we were having like 100,000 transistors or 1 lakh transistors. Now we have we have almost 50 lakh to more than 50 lakh transistors on a single chip. Now it is very difficult for us to actually optimize these designs at the digital level, but AI again can help us in doing a lot of optimization. So the following optimizations can be done using AI. One is the data path optimization. So what is data path optimization? So for example, you have a data path, like let's say from one flip-flop to the other flip-flop, you have a huge combinational logic. So previously we used to do synthesis, we used to get the gate count, and then we used to go and try to optimize the RTL manually. But now AI tool itself can tell you that okay, this combinational logic is very high, and you can actually optimize the design much before. So at the architecture phase itself, we can do a lot of optimization using AI. So in the coming slides, you will see that we have a lot of optimization techniques using AI. The second is the resource allocation. So typically, if you see, there are a lot of resources which are consumed during synthesis and during PD, right? So all the resource allocations are also typically you can optimize using AI. Again, that there are many tools which actually help to do the resource allocation. Similarly, ALMs. So these logic modules in FPGA, ALMs is like typically the logic modules which are used in FPGA, and For example, even we when we are working on FPGA, there are a lot of ALMs that actually get consumed when you do a complete an IP design, right? Now AI will help you to actually reduce the ALMs in the FPGA using again optimization techniques, using the AI tools that we have currently in the industry. Then the most important thing is the power optimization. So typically power optimization also is one of the very key feature in AI. As all of you know, the design complexity is increasing day by day, and the power has become a huge challenge for a lot of chip design folks, right? So typically one of the biggest challenge that we are facing right now is the power optimization. So AI can also help. So all these things were happening, but they were happening manually. Now because of AI, we are actually doing a lot of things, automating a lot of these things in the VLSI design flow. Then we can also have, as you all know, so we use AI tools, but inside AI tools we have the machine learning algorithms which can comprehend the design specification, performance goals, and etc. So we are not too much, so we are like the end user for ML. We don't write the ML code, but we use a tool that already uses, or that already they have written the ML code. So typically even when you use Synopsys tools or Cadence tools, we don't write the software. We are basically the end users of the tool. So that's the software, the people who write software or machine learning programs or machine learning algorithms is a separate team, right? So we are the ones who actually use these tools to optimize our designs, to make our designs more efficient. So machine learning algorithms can comprehend, they do a lot of stuff. They are the most intelligent algorithms, but unfortunately or fortunately, we do not actually write any ML algorithms. We only use the tool, the AI tool. Okay. Then coming to the physical design optimization, then then coming to the physical design optimization, we have like four typical areas in the physical design, as all of you know. One is routing, the other is placement, the other is floor planning, and then there is a power optimization. So we can actually do, or we can use AI tools to improve the physical design, operations or efficiency in routing, during routing, placement, even during clock tree synthesis, floor planning, and power optimization. The same things that we can do in front end, we can actually also do in the physical design. So these are some of the areas where AI can actually effectively improve the physical design efficiency. Then we have the machine learning algorithms, but again, as I mentioned to you earlier, we don't write any machine learning algorithm. Machine learning algorithms are typically integrated in the AI tools already, but they can optimize chip layout, timing closure, signal integrity analysis, clock tree synthesis. uh, so all these things they can actually go and, so if you see here, clock tree synthesis AI algorithm considers Q and power consumption for selecting the right clock tree structure. So previously, clock tree structure, we used to manually select which clock tree structure we should be using for our clock tree designs, even though we have tools, but we still have the flexibility. But now AI or the machine learning algorithm can actually help us to select the right clock tree structure to get the maximum benefit out of it, or get the maximum optimization out of it. So these are the different advantages of using AI tools in the physical design also. Okay, I will move to the next slide. So fast design exploration and innovation using AI. Now AI driven behavioral synthesis. I'm not sure how many of you are aware of synthesis and behavioral synthesis. So typically behavioral synthesis can do like higher level of abstractions, and designers can work at a more abstract level, focusing on functionality rather than low level details, like how many gates have come, how many gates have been inferred, or how much optimization we have to do. So AI is actually now driving the complete behavioral synthesis, which previously the designer used to do. So designers like us used to typically take it through the synthesis flow manually, check what is the gate count, and lot of manual things now is getting automated using AI. Okay, so and it also function focusing on functionality. So previously, when you if you people know what is synthesis, typically we don't worry too much about functionality unless we do a simulation. During synthesis, we just take whatever RTL code we have and we run it through a synthesis tool, and then we manually start analyzing each of those reports. But now AI can do all the analysis for you in the synthesis phase itself, and it can actually help you to identify where the logic is more, where you have to optimize, or where there might be a timing issues or timing errors, timing bugs. All these things will be now driven by AI. Okay, so very big. We are going into a paradigm shift from manual efforts to a complete AI driven behavioral synthesis. So this shift in perspective enables faster design exploration and innovation. So there are a lot of innovations that we can spend time on. So previously, let's say you have to tape out a chip in 1 year, you don't have so much time to go and actually do some innovation also in that chip. But now, because the time to market has reduced, so AI is actually helping you to actually do more innovation. Machine learning models can learn from existing design and propose structures that can actually match already integrated. As I said to you in my previous slide also, we don't do anything on the machine learning side as such. But then there are VLSI industry people who are working on the software side of things, who may be integrating these machine learning models into the tools and into the AI tools. So this can lead to more creative and efficient solutions. So finally, what is the goal of any chip design is typically it should be very efficient. The cost should be as minimal as possible. We should have as many good chips as possible compared to, so the ratio between the good and the bad.
Hello, sir.
Can you hear me?
Yes, sir.
Sorry, I lost my network connection. There's a power cut here. Can you see my screen?
Yes, sir.
Okay. So I was talking about the fast design exploration. So there's a lot of make it more efficient for us to execute designs, and also will give us a chance to do innovation. So can you? I hope I'm not muted. Yeah. Okay. Okay. And then we have something called as predictive modeling and fault tolerance using AI. So AI plays a very crucial role in predictive modeling. What is predictive modeling? Typically, like let's say you use 10,000 vectors to test what is the code coverage in your design. So AI will do predictive modeling and will actually let you, like, make you like get the same coverage using like 5,000 vectors, or maybe 4,000 vectors or 3,000 vectors, depending on what the design is. So typically you are reducing your effort to get the code coverage by almost 50%, more than 50% using AI tools. So AI plays a very, very crucial role in predictive analysis, modeling for VLSI design, also predictive analysis. So predictive models are often based on neural networks, can estimate the performance of a design even before it is physically implemented. This capability helps designers identify potential issues early in the design and thereby reducing the cost and the need for costly redesigns. So every realize I think especially, right, it's a very costly affair if you don't catch the bugs early. Let's say after the chip is taped out and then you catch the bug, then it is a very, very big loss to the company, to the society, to the everyone, right, to the designers, everyone. So now AI is trying to actually reduce that gap. So it is trying to help you to catch the bugs much faster than how much time you would have taken to do it manually. So AI also contributes to fault tolerance. So fault tolerance is again, as all of you, I told you before, it is a part of the DFT, design for testability, and we do a lot of fault tolerance models in our designs. Now these fault tolerance models also have been done a lot of things manually. We actually go and identify the faults and then fix them. But now AI will actually help you to identify these faults, and it actually reduces a lot of efforts to to fix those fault tolerance issues. So AI algorithms can suggest modifications, and also like it will make your IC more robust against different faults. So AI is so powerful, as you can see, right? So without AI, you cannot even imagine now, because as we go and move to the next era of designs, they are going to be very complicated, and manually debugging all these things is not going to help. Even if you put 10 engineers on a single chip, it will not help, because it cannot do like an AI. We still depend on AI for this. Again, for analog and digital circuit designs, also we have AI. So AI can aid in logic synthesis using various AI tools available in the EDA industries. In the analog circuit design, AI can help in sizing transistors. So as you all know, transistor sizing is one of the key areas for power. So where the power is very highly consumed, typically one of the way to reduce the power is resizing the transistors. Now AI will actually help you to identify which transistors to resize, or probably help in resizing the transistors. So AI is again save a lot of time over there. Okay, so these are some of the AI tools that we have, which can actually do a lot of help us on a lot of design techniques. So if you see, what is the category like design automation, what does it do? So the applications are synthesis, optimization, placement, and routing. Design space exploration, which I just showed you in my earlier slide. This means you are actually basically reducing your architecture and parameter tuning. So architecture is going to be a very big. So every time you start a chip, right, first thing what we do is typically we work on the architecture. If the architecture is good, we can guarantee that the chip will be good, or the chip efficient will, you can actually generate an efficient chip. So design space exploration is one of the key things for any chip design, and fortunately now AI is actually helping a lot on the architecture side. So previously, let's say some part of the chip, right, is consuming a lot of power. So what do? We go into there, we go and insert some clock gating cells or power gating cells, and then try to reduce the power in that by adding some logic. But now AI will actually do that for you. So you can feed in your architecture document to AI. It will take the architecture document as the input, and it will do all the analysis for you, and it will tell you that this part of the architecture consumes more power. So you can actually go and change your architecture accordingly. Same thing for verification and validation. You have, as my previous slide showed, ATPG, automatic test pattern generation, debug automation, coverage analysis. So all these type of things you can do and reduce you can reduce a lot of time to debug. Then you have power and performance. So low power design, dynamic voltage and frequency scaling, DVFS. Then we have the EDA tool enhancement. So we have now intelligent CAD tools like VSO.ai. So VSO.ai is the tool that I am currently using for AI based tools. This is from Synopsys, and we also have a DSO.ai, design space optimization, from Synopsys. So we use so many EDA tool enhancements has come up for us to help in our day-to-day debug. Then yield and manufacturing. So you can also do a defect prediction, you can do a process variation analysis and lithography simulation also using AI tools. Then you have like hardware security, like any virus or any Trojan detection, and then IP protection also. You can use AI to make sure that your IP is, somebody is not violating the IP protection rules laws, right? So reliability analysis. So if you know that your chip is already getting too old and you need to throw it out or something like that, so it will also give you an aging and failure prediction that okay, this particular chip is already like outdated, and then you need, so a lot of things where you are automatic, right? Automating things. Previously everything we used to do manually or tool based, but now AI is actually helping you to automate a lot of these things. So AI specific hardware, neural processing units, NPUs, custom accelerators. As you all know, right? Why Intel lost the race to Nvidia? Because of AI, right? AI was introduced by Nvidia much before than Intel into their GPUs, and it took some time for Intel to integrate AI into their processors. So that is the reason why we lost the race to Nvidia and other companies like AMD. So AI is a very big thing. Okay, so please make sure that you people update to AI tools instead of using the conventional EDA tools. So last two things are data analytics and debugging. So we can also do a lot of big data analytics. So you might have heard a lot of names like big data in the software side. Now we use the same big data analytics using AI to do our post silicon debug. And then the life cycle management, like predictive maintenance. So it is same thing like the reliability analysis and life cycle management. They are more or less the same. So you can do a predictive maintenance, like how the chip, whether the chip is aging and what is the whether we need to still use it or whether we should put it to EOL. It is called EOL, which means end of life. So all these things are some of the applications of the AI tools in VLSI. Then we have so these are some of the AI driven EDA tools. Okay, so we have Cadence, Cerebrus from Cadence. Okay, uses AI and machine learning to optimize digital chip design. So the name of the tool is Cerebrus, and it is from the company Cadence. It focuses on power, performance, and area. Typically, it is called PPA. Cerebrus learns from past projects to improve efficiency. So some of these AI tools use your past project experience or past project data to actually get to improve the efficiency of your current projects. Then, as I mentioned to you, Synopsys DSO.ai, design space optimization. This is the current tool that I am currently working on, the DSO.ai, and it employs AI to optimize the design space for low power, high performance circuits. It automates exploration to identify the best configurations for power reduction. So everything, right? We don't have to manually go and see which configuration is the best, or which area, which part of the chip that we have to reduce the power. Everything is done by DSO.ai. DSO.ai is so powerful tool. It can even help you in your architecture. So even your architecture documents, you can just give it as an input to the tool, and it will actually tell you, no, this architecture at this point is problem, go and fix it, like that. That is so intelligent, the Synopsys DSO.ai. Then the Siemens Caliber with machine learning extension, so offers machine learning capabilities for design DFM checks, including power aware optimizations. And then last but not the least, ANSYS Red Hawk. So it provides power integrity and thermal analysis with AI capabilities for identifying hotspots and optimizing power delivery networks. So all these tools are typically helping us in VLSI design. But right now I am only using the Synopsys DSO.ai. But if you people want to explore all these tools, I think it's a wonderful opportunity, and you can understand how how important it is to migrate to AI tools, because manual effort takes long time. So I think I have a couple of slides to show you how much how we have reduced the time to market for each of these by using the Synopsys VSO.ai. Okay, power modeling tools. We have MATLAB with AI ML toolboxes. So it allows the creation of custom power models using machine learning and integrates with VLSI tools for. So if you see, MATLAB earlier previously was a separate tool, and we used to typically use MATLAB for mostly our testing our algorithms and other things. But now they are integrating AI into MATLAB as well. So AI is everywhere. Okay, that is the fundamental message of this session. AI is everywhere. So you take any tool, they are integrating AI into them. So Power Pro by Mentor Graphics focuses on RTL power optimization and analysis, leveraging AI for power reduction early in the design flow. So the reason is, I think all of you know that power is the biggest challenge in the current industry, right? So if you see your phone, you want your phone to work for long times, even though you know the battery life should be more. So all this is typically gives way for AI to help us to reduce power in the very early stages of the development. So AI will tell us before itself that okay, at the architecture stage or the design stage or at the micro architecture stage, that no, okay, this is the place where you should reduce the power. And then we go and you know the designer goes and optimizes the power in that particular domain. So the idea is basically to catch the power reduction in a very early stage in the design flow. Then you have the Apache Power Artist, so industry standard tool for RTL power analysis and optimization. So everywhere you see power analysis, optimization, because these are the two major challenges in the VLSI design industry for any designer, right? So often complemented by custom AI solutions for deeper insights. So all of us should be aware that power modeling tools and the optimization and the architecture optimization tools are now driven using AI. Okay, so I want to give you an example of one AI tool that we have already used in the VLSI industry. So Synopsys VSO.ai. Okay, if you are not able to see, let me. So VSO.ai is verification space optimization. This is a tool from Synopsys. So as you all know, if you have done regressions will take a long time. They take, like, some designs usually take even 1 week, 10 days to run, depending on the complexity of the design. Okay, regressions are optimized so that high ROI, return on investment tests, are run first, and analysis is automated to define the prescribed insights. What this means is that now you run a design, you run your verification regression for 1 week, and then you see that, oh, the coverage is like 30%, and then you go back and then start debugging your test bench, and you can see like why that coverage is 30%. Have I not written something in my test bench? Have I not written anything in my test plan? Then you, lot of manual analysis, right? But now what is happening is you run VSO.ai, the same regression that you are running manually, you run using VSO.ai, and VSO.ai will tell you that, hey, no, you don't need to run 25,000 tests. You can just run 5,000 tests and you can get the coverage of 50% already. You don't have to do anything. So same thing will happen for the DSO.ai. You go manually, you analyze what is the issue, and then you go and typically go and debug it manually, and then do a lot of work, right? But you tell DSO.ai, hey, I want to optimize my power here in this chip, and then DSO.ai will actually go and run the complete suite for you, and it will actually help to identify that, yes, this is where the problem is, so please go and fix this. So that is called ROI, return on investment test. So you actually, if you see in this diagram, you can see like prescriptive insights, targeted stimulus, automated test biasing, regression optimization, and automated analytics, AI inferred coverage. So typically AI inferred coverage will do all these stuff for you, which we have been doing manually. So prescriptive insights means it will do a it will do a like prescriptive analysis, like, okay, these are the tests that we don't need to run to get, like, 80% coverage. Similarly, automated analytics. So you don't have to go and manually do the analysis. The VSO.ai will actually go and do the automated analytics. Similarly, regression optimization. Regression takes the maximum time for any one of us to run thousands and thousands of tests. I am just saying 10,000, but there are 50,000 tests, 100 lakh, 1 lakh tests, 2 lakh tests for very complex chips. All those tests, right? AI will help you to reduce by almost 50%. So whatever we did experiment, we could reduce the tests by almost 50%. So okay, so these are the four data analytics which happen inside the tool in the VSO.ai. So descriptive, like what happened, diagnostic, why did it happen, why did the test not hit, predictive, what will happen if I rerun this test again, prescriptive, what should we do, what is the fix that we should give. So descriptive, diagnostic, predictive, and prescriptive analysis is completely now done by AI. We don't have to do any of these. Previously we were doing all these, and now AI tool will actually do it for us. Okay, so I will not go into this data analytics too much. So VSO.ai. Okay, so I will spend the last 5 minutes over here. Okay, 70% of the design cycle is verification, right? So shifting from manual to automation is applying VSO.ai. So why do we need to apply VSO.ai? Why should we use VSO.ai? Because we want to move from manual to automation. Attaining the best coverage result with quality is the biggest challenge in the current verification environment. So I'm not sure if you people heard about coverage, but coverage is one of the most important aspect for any verification engineer. 100% code coverage, 100% functional coverage means that your quality is very good and you have already verified the design. But we are not reaching to 100% every time we are stuck at 90%, 80%. After running regression for almost 1 week, 10 days, then we come to see, oh no, we have only hit 80%. But now VSO.ai will actually, if you see my last bullet, VSO.ai has shown significant benefits by reducing the number of tests by more than 50% to achieve the 100% coverage. So you can imagine if you run a regression for 10 days, now you can hit the same 100% coverage using VSO.ai in 5 days, which means you already saved a lot of time. 5 days is not a small number in the VLSI industry. Okay, it's a very, very huge number. So if you see here, right, you can see my chart, like how much we are seeing. So 10%. So typically there are two designs which I have taken here, design one, design two. So if you see here, the orange one is the manual one. So the blue line is typically the the coverage by VSO.ai. So you are hitting 10% higher coverage in half the number of tests. So if you see, you are getting more coverage and your also tests have reduced, the blue line. The orange line is typically like the manual thing that we are actually doing so far. Similarly here also, if you see, it takes about 3000 tests or maybe more than 3000 tests to hit the coverage. But if you see here, within 50% of the tests you are able to hit higher coverage. So this itself shows that VSO, how much AI is already playing a very huge part in the verification process. So I have only slides for VSO.ai. I have not put anything on the DSO.ai because DSO.ai is still premature. We are still doing a lot of stuff on that. Okay. So if you see here, right, VSO.ai results, we are running 1798 tests to get the functional coverage of 98.76%, a code coverage of 99.4%. Code coverage includes line coverage of 99.44. Code coverage, which is toggle coverage, is 94.92. Code coverage FSM is 100%, but you have run 1798. Now, if you go to the right side of the table, now we are only running, so when you enable the VSO.ai, now you are only running 565 tests. You hit a functional coverage of 96.55, which is almost equivalent to the one that you hit with 1798. But if you see the remaining ones, right, it is almost the same, 99.44, 99.44. Code coverage 94.92, 94.86. Code coverage FSM, you get 100%, 100%. 98.96, here you get 98.79. So if you see, right, more or less with so much, almost 1/3 of the tests you are actually hitting the code coverage and functional coverage almost the same. So which means you can imagine how much VSO.ai is adding value to our work, right? So this is some of the results. So this is the future of AI in VLSI. With the growing complexity of chip designs like AI accelerators, 3D ICs, the integration of AI will continue to expand. So as I mentioned, as the designs are getting more and more complex, we need the help of AI to help us to reduce the time to market. AI will help to automate more stages of the VLSI design flow while improving quality. So whatever I have shown you so far are just maybe one part of what AI can do for us. But there are many things which are going to come in the VLSI design flow, and AI is going to help to automate most of these stages. AI will soon contribute to designing the next generation of processors optimized especially for AI workloads. So as you know, NVIDIA has already gone into AI GPUs, AMD has integrated AI, Intel is now integrating AI. So a lot of these processors which are going to next generation processors which are going to use neural processing and all that stuff, right, will actually use AI. So you can imagine that the future of AI is certain, but how much we are going to use AI in our lives is what we have to determine. Like we have to decide, okay, that we have to. It's time for us to move from manual testing to AI testing. AI will soon reduce the time to market for complex chips, thereby creating more profits for the product companies like Intel, AMD, NVIDIA, and other things, right? So we are, as you see previously, 50% of the verification cycle is reduced, which means if you take a chip to tape out in 2 years, you are actually doing the tape out in 1 year, right? So that is the power of AI. So 1 year means you make huge profits. Like the same chip is coming out in 1 year, you are already making like huge profits. AI will also automate most of the VLSI flows as seen in the previous slides like RTL, synthesis, PD, and DFT. So already we are seeing that verification, there is a lot of optimization happening because of AI tools. Then there are a lot of AI tools in RTL, then synthesis, PD, and DFT, which I have shown you in the earlier slides. So AI will automate most of these flows, right? So we will see that every flow, whether it is RTL, DFT, PD, analog layout, analog design, everything AI will be entering in. So my suggestion is here that all of us, we will need to move to the next generation of methodologies which use AI. So it's time that we start integrating AI into our VLSI EDA methodologies. Otherwise, we are going to fall behind the race and we will not be able to complete. So the same design, if we take 2 years, we will continue to work on the same design for 2 years if we do not start integrating AI into them. If you start integrating AI, then it automatically becomes like 50% already reduction, and then you already save like 1 year turnaround time to actually tape out your chip. Yeah, so with this, I think I have taken 1 hour and we have come to the end of the session. So I hope you people are there. Madam, are you there? Can you hear me?
Yes, sir.
Yeah. So So any questions, madam?
So, dear participants, if you have any questions, you can ask. Are there any questions?
If no questions, then I think yes, we can.
Hello, sir. Can you able to listen me?
Yes, sir. Yes, sir.
Okay, sir. So this is Mohammed Mian from Abdul Engineering College, Tamil Nadu.
Yes,
Sir,
sir.
when you are using this AI tools and every now and then we are in requirement of systems with a higher performance grade GPUs and all.
Mm-hmm.
And there are certain things that you have told. What can you suggest? What configurations we can use for that?
What configuration meaning?
What configurations is our system configurations to use these tools?
So this is nothing. So the same configuration. So system configuration is doesn't matter. I mean, this if you already have some Synopsys tools installed in your system, which can already
Okay.
support your current Synopsys tools. So Synopsys has not given any special configuration. So the license comes along with your conventional Synopsys tools, just that they have added the AI capabilities into their tools. So you should not maybe while requesting, maybe they may take some extra money for having the AI tools, but otherwise from the configuration point, whatever configuration you are currently using to support your Synopsys tools, the same configuration will be applicable for VSO.ai also.
Okay, sir. Thank you, sir.
Any more questions?
Sir, I am Dr. Umar Taragan from Basilius College, Kerala.
Yes, sir.
And I was in ISRO earlier. And my question is, why should we consider verification as a separate entity rather than using AI along with the design? So there should be one day when this will be considered as a single entity, and the entire thing can be done at a single command.
It's a very good question, sir. Thank you for asking. So typically what happens is, sir, if design and verification fall under the same category, then there will be a lot of bias. Like for example, if let's say I'm designing one chip or I'm designing one processor, and I will only have my team to verify the processor, then I will be biased because I will put my test bench or I will
Sir,
write.
excuse me. What I meant is not that I question, because it is done by AI itself. So there is no question of I or you. No, the second I will be different from the
So
first
when
I.
I'm saying
That is
I
what I
means
meant.
when I'm saying I means the designer cannot verify his design. There
Yeah, that
should
is
be a
what I
separate.
meant also. Because this AI should look into both aspects. AI as a designer, as well as AI as a verification engineer. That's what I meant.
Yes, so verification engineer will use the verification side, verification tools, and designer will use the designer tools. We can, because design verification.
Exactly, that is what I meant, sir. What I
Yes,
meant
sir.
is that these two, why you cannot combine along with the design itself, these
They
should
cannot
combine.
be.
These
They cannot
two
be.
entities to work coherently and find out
Yeah,
the
they cannot
issues.
be. They cannot be combined because they are two separate things. You cannot combine design and verification and PD because PD is
I
different. Design
understand,
is
sir. I
different.
understand, sir. But I think you didn't get my point.
Yeah.
Rather than going for a second level of verification, it should go coherently so that this AA first part, the role should be as a designer. The second part, it should be as a verification. So it should go coherently and find online the defects and all. And when it is chip is manufactured, it is a full suite which has taken care of the entire design process as well as the verification process. That's what I meant, sir.
So maybe Synopsys may integrate everything into a single suite. I'm not sure on that, but for now they don't have a single suite which supports both design and verification. Right now we have a separate suite for design and we have separate suite for verification. Maybe in the future, maybe I don't know if Synopsys like feels that okay we can have one, because as you said, right, for PD now they have actually combined PD and timing into a single tool, which is Cadence Genus, right? Genus now. Previously, we used to have RC compiler for doing synthesis, and we used to have a separate tool for the PD. But now they have combined everything into a single tool, which is called Genus, GENUS. Okay, but say maybe they may do the same thing moving forward, Synopsys. But right now, we do not have any single solution for both design and verification, because one thing is the coverage that verification people work on typically is a separate. They have a separate test vectors for that, and they have a separate thing for that, so they cannot use like design, they cannot combine it with design for that same reason. That is why VSO.ai, which is a specific tool, is based purely for coverage. It only does purely coverage, so coverage cannot be combined with design. So there are some things which cannot, maybe verification, yes, If you want to run at a high level, like to make sure that your design is okay, then you can use this test vectors combined with design. But for coverage and power reductions and all that, you have to have a separate, because architecture is like, your architecture is not a single architecture which combines everything into a single chip. It actually partitions your design and it partitions your verification separately. So in VLSI, my experience is that partitioning the design, partitioning the verification is much more efficient than actually having both of them using a single tool for both design and verification. But if something comes up later, if they are planning to integrate both design and verification into a single suite, then it is good. Then we don't have to actually, we don't have to do multiple phases of verification.
Thank you, sir. But my doubt is still at a higher level of abstraction. That is, we are not looking into whether it is synopsis or cadence. I am looking as a policy matter. The entire design and verification. That means your slide started with genetic algorithms, right? So in that itself, this genetic algorithm, in that way, it has to be that suit or your the design verification should go adaptively, and then when the product is realized, it has got, as you told, 100% toggle coverage or 100% path coverage or whatever it is, and the total this thing coverage should be 100%.
Yes,
in that way, we are thinking in that direction, not with respect to any tool or whether my thought process is correct. That's what I asked.
Actually, I don't agree with it, because we still, for me, see, I am a designer, so for me, I still think at my design side only. So if you are asking whether at a genetic algorithm whether we can combine both of them, I don't have that experience to think how it works.
I put it as an example only, sir.
Yes, sir. Yes, sir.
It is not that we should use it as a policy, that matter only. I'm not biased towards cadence or this thing, synopsis or anybody. But only thing is that as a policy matter, whether we can do it in a higher level, not thinking with respect to any company. I'm thinking as a designer of the entire suite. That's what I'm doing.
So I will tell you, I will give you one simple example, sir. Let's say, like, you have a design, okay? You have a complete full SoC, which has a microcontroller, which has a microprocessor, which has analog, which has digital, everything, standard cells, everything, okay? Now, if let us say everything is in a single, which we are actually going to in a single die right now, but I'm talking from a design side, okay? Let's say we have a complete SoC, everything is in a single RTL, or let's say in a single design, everything. Then let's say there's a problem, right? If you face that let's say the processor or probably the microcontroller is having some some bug, and it is not working properly. So do you think it is easy for us to basically debug the complete system if it is like a single system, or it is better that the design is partitioned and then we debug each of them separately?
Sir, sometimes I might convey it to you in a different way. The problem is that as soon as as you rightly told, as soon as the SoC is raised, the entire process should be completed. The fabrication should be verified. That is the world I am looking for. Whether my thought is correctly, I want to find.
Okay. Yeah. So I
am not seeing when your SoC or microcontroller this thing is realized, that should have undergone all the verification process, and also this ATPG or ATPG, whatever it is, that also should have been exercised, so that no fabrication related faults are also occurring. That is what I meant, sir.
Okay, sir. Okay, maybe it's a good idea, but I'm not aware about that at this moment.
No, I am just proposing to you. That's all.
Okay, sir. Sure,
okay,
sir.
Nice of you. Thank you, sir.
Yeah, we will discuss it separately, sir, again.
Thank you, sir. Thank you, sir.
Thank you, sir. Yeah, madam, any further questions? Otherwise,
any more questions? So I think we can conclude this session. Sir, we extend our sincere gratitude for your insightful session, sir. Your expertise and perspectives have greatly benefited our participants, and we look forward to future collaborations with you, sir. Thank you so much, sir.
Thank you, madam. Thank you, everyone.
My personal thanks also, sir.
Thank you.
No problem, sir. No problem. I think we should get in touch later. I will connect with you, sir.
Yeah, sure. Sure,
Thank you.
sure,
Thank
sir,
you so
sure.
much for your input, sir.
Thank you so
Thank
much.
you, sir.
Thank
Bye,
you.
sir. Bye. Bye, madam.
Bye, sir. Thank you. Let us move on to our second session of the day. Our second session for today is by Dr. S.K. Noor Mohammad, sir. Dr. Noor Mohammad, sir, PhD in Computer Science and Engineering from IIT Madras, holds over 21 years of teaching and 20 years of research experience. His expertise spans computer architecture, reconfigurable computing, VLSI design, hardware for AI, signal processing architectures, and high performance computing. He has executed 7 sponsored projects, 19 industrial consultancies, fabricated 3 chips, and designed 4 products. With 42 SCI and 44 Scopus indexed journal papers and 60 international conference papers, his research footprint is significant. He has guided 8 PhDs, established advanced laboratories including HPR-CSC and the Software Security Lab, and mentored over 90 student projects. Beyond academics, he has organized 18 national FDPs, introduced innovative elective courses, and held key administrative roles at IIT Kanchipuram. With great expertise in this area, Sir will certainly provide us with practical insights and deep understanding. Let us welcome our speaker for the session. A hearty welcome, sir.
Yeah, thank you, madam. I hope am I audible to everyone?
Yes, sir.
Okay, thank you very much. Good evening, everyone. I hope all are doing good. Okay, let me share the topic. So I'm going to talk next 1.5 hour about AML for VLSI design, and so what is the changes that happen in the AML uh, implementations, means AML usage in the VLSI design. Those things I will be detailing covering. I hope now you are able to see my screen.
Yes, sir.
Okay, thank you. Yeah, let me thank you for giving the opportunity to discuss about this topic. Okay, let me make it full screen. Yeah, so next 1.5 hour, I am going to talk about how AML is used in the VLSI design, and such that we can build one efficient VLSI design circuits. Okay, that's something what I am going to cover here. When you talk about VLSI design, again, you can understand that we need to concentrate on the 3 major parameters. So that something is area, power, and delay. So this is the 3 key parameters which we always target to optimize it. There are some cases we can optimize the power. There are some cases we can optimize the delay, and there are some cases we will optimize the combination of any 2 parameter. That's something what typically we do it. And if you look at the conventional tools, whatever we are using, which is not working with the without AML approaches, it is going to have a different kind of algorithms. Mostly we'll use some kind of optimization algorithms. That's something what we are using to build the designs. Okay, but when AML has been become one of the key technologies, the benefits are very good, and where we could optimize the circuit in a better manner. Okay, and there are some areas which still beginning stage where some of the improvements can be done, and such that even we can enhance the designs, because chip designing is the most complicated task because it involves a lot of parameters which we need to fine tune it. And when you talk about the complexity and more parameters, and again historical data, in that case this AML techniques are definitely is going to help us. Okay, so with this note, let me start. I'm going to talk about in this lecture for beginners to make understand what is the basics of AML and what are the types are there. So those things I will cover briefly, and then followed by the some of the fundamentals related to VLSI design, and then how AML is applied for different stages in the VLSI design flow, such that we can optimize the parameters, such that we can enhance the uh, performance of the chip. And even we'll also talk about some of the real world tools and frameworks, and some of the case studies also will be discussing in this lecture. Okay, so this is the things, and then we'll also see that some of the challenges and future directions with respect to the this domain. Okay, so this is the objectives that I'm going to cover in this topic. So let me introduce what is AML. I hope you AML is one of the buzzword in today's context, where everybody wants to learn this, and so where we want to simulate the human intelligence in the machine. That's something what we call it as a artificial intelligence. And when it comes to the a subset of that one is going to be a machine learning, where it enables the machines to learn from the data. Again, I will have some kind of data. We also call it as a historical data, and it can be labeled or it can be unlabeled, and from that I will extract some information, and from that I can make some decision. Okay, so that's something what we will be doing when you talk about machine learning point of view. Okay, example is, if you look at Gmail spam filter learns that millions of messages to detect the spam. Again, the messages which is not contextual, and which are all irrelevant to the my subjects, so those things will be detected as a spam. That's something what we can call one of the example here. And again, the way it does is we will have a predetermined patterns, which we call it as a uh, historical data, and those patterns will be compared every time whenever a new spam comes, and whenever it patterns matches, then we'll label that one as a we'll label that one as a spam. That's something what we'll do here. We'll classify that one as a spam. So this is the one of the example, and another simple analogy is just like a student improves the by practicing more problems. Okay, so he can learn the more concepts. The same way ML models will get better when you have a proper data, again proper realistic scenario captured data. That's something, if you are using that in your machine learning models, so then it will give the correct scenario, correct output it can produce. Okay, so this is a brief about machine learning and AI information, AI related. So now we'll talk about what is VLSI design. Again, I hope VLSI is something which we are using. We want to integrate millions of transistors on a same 1 centimeter, 1.5 centimeter, 1.5 centimeter, such that we can build a processor or build any kind of custom circuit, such that we can operate it and get the whatever the functions I want to implement in the circuit with a smaller delays, and such that I can meet my timing requirements of the any application. That's something I'm using here. So now let's understand why VLSI is uh, we have to consider here, is because so we want to design a very compact chip, which means a small size, which will be of, as I mentioned, that 1.5 centimeter, 1.5 centimeter kind of chip, on such a way that it should deliver a very good performance. That is performance in the sense high speed characteristics. Especially if you look at how we can measure this one is when you talk about your processor. So typically the processor performance we measure in terms of clock speed. So I hope you know that my processor speed is going to be, let's say today's context is around 3.8 to 4 gigahertz. Around that it will be there. So that's something what my processor speed. It means if you take 1 by 3.8 gigahertz, okay, that's a clock width I will have. Okay, and in that clock width I'm going to do one operation. I hope you are understanding what I'm trying to convey here. So when you take a 1 by, sorry, so when you take a 1 by whatever the frequency that you are having, so that is going to be a 3.8 gigahertz if you take it. So let's say around it is 4 gigahertz, and let's say in case of 4 gigahertz, what is the thing it will happen is it is going to be 0.25. So that is 0.25 nanoseconds it will come. Am I right? So it will have a 0.25 nanoseconds. So that's something what will happen here. In that 0.25 nanoseconds, I am going to perform one operation. So that's a power. That's something what we'll do here in this case. Okay. So it means what is our object is we want to have a higher clocks. That's something what good performance I needed. Again, is it really good performance? Is something is a matters today's point of view. If you say that yes, 100% I need a performance, but we cannot go for very high clock rates. That's another biggest problem. The reason is the energy consumption by the chip is going to be very high. Okay, and if I operate my processor or anything which is going to be in a higher clock rate, let's say that somebody has designed a 6 gigahertz or 7 gigahertz like that. Yes, it is possible. As a hardware designer I can do it. Okay, but the point is that my chip, whatever the number of operation I'm doing, whatever the heat it is dissipated on the silica material, it has to dissipate quickly and send it to the environment fastly. If it is not happening, then chip may burn out. Okay, so that's the reason why today, again, once upon a time, energy only high speed design is the one of the constraint, but today's context, energy efficient design is the one of the key factor that we always consider. It means we'll have a key trade-off between energy versus performance. So that's something what we'll consider in the design, and at the same time we want to have we will measure the performance today, not will always say that what is the energy per operation consumption. So that's a key metric. That's something what we'll take, and with respect to that we'll measure it. Okay, so this is something what we are doing. So if you look at here in this case, I need to consume the I need to estimate the power, I need to estimate the delay, and what is the energy per operation I need to estimate it. And with respect to that only we can tell that how good my designed circuit is. And as you know that when you talk about VLSI design flow, it starts with the specification of the circuit, and where I will specify the my circuit behavior, and the specifications I will tell. Will have a specifications, and from the specifications we'll consider that what are the behavior of the circuit, and those behavior will model in a register transfer language. So that's something what it talks about. I'm converting my specification to register transfer language, and once I convert this specifications and behavior into the register transfer language, that's the RTL model we call it, and then this RTL model will be synthesized into converted into a gate level netlist, and then from that gate level netlist it will be converted into a switch level netlist, and from the switch level netlist it will be converted into a layout. Okay, and whatever the layout I get, that's something what I will do the placement and routing, and once I do the placement and routing, I will generate a GDS2 format, that is a graphical description standard 2 format, which I am going to give it to the fabrication unit for fabrication purpose. So typically my VLSI design flow in a precise manner. We'll have a, these are the processes in that, that is a specification to RTL, RTL to synthesis, and synthesis again. We'll have a gate level synthesis, logic level, circuit level synthesis, and layout level, and then we'll have a placement and routing. And once that is done, we'll go for a fabrication. So in every phases of the VLSI design, where there is a optimization involved, because I am optimizing such a way that one of the key concern is I want to consume the lesser area, and when I want to consider the lesser area I want to consume, then uh, means if I design the circuit which a lesser area, my energy consumption will come down, and uh, my critical path delay, whatever I'm using in the circuit, it may also come down. So that's something what we'll keep as a target, and that's how we'll do this design. And examples for this one is where we use chips in the smartphone, laptop, smartwatches, all these things which we build by using VLSI design. So now, so we understood what is VLSI design flow. We understood what is AI and ML techniques. Okay. So now, why we want to combine AI, ML with machine learning? So that's something what I am going to give the reasoning here. So if you look at my traditional approaches that we are using, that is traditional flows or manual approaches it uses, and it also uses time consuming models, especially when you talk about VLSI circuit design, where we are estimating the power models, okay, even delay models. So we have a different approaches which we are going to use it. So approximately there are Elmore models, there are different models which you are studying in the Neil Weste textbook of VLSI design course. Okay, so these are all the standard models which we use it, and it itself has a lot of challenges, and in the implementation point of view, again with respect to the time it takes to consume, and even which one is the more accurate, that is also a big study. So which model will take miss how much time, and which is going to be more accurate to the my original design. Okay, because why we have to do this one is in the design flow, in the VLSI design flow. So before we fabricate the chip, I want to estimate that what is the power consumption of the chip, and I want to estimate that what is the delay that it is going to consume. It means critical path delay, that is from the input to output. Okay, these are all I want to estimate by using my mathematical models. Okay, that's something what I am building in the my VLSI automation tools. So those things I am using and I am estimating it. So when design so that's something what I am doing. These are the point one here is first point is here, all these conventional models, traditional models are time consuming, and these are all manual processes it is going to be. Another thing, the complexity of the circuiting, when complexity of the circuit is increases, scaling is going to be a very challenging. So that is again this again scaling with respect to the computation point of view. Okay, what is the total power? This are all is going to be again is a challenging. So it's also a complex. So this is another issue when you talk about conventional tools. But if you are using a AML techniques, because whatever the models you are using, mathematical models, okay, for estimating the power, for estimating the delay, for estimating the area, okay, and these things even, you can simplify, you can automate it by using a AIML techniques, and even you can optimize the which is the right standard cell that I have to use in my design. So that also you can choose here. Again, you know that the same functionality of the standard cell will have a multiple characteristics will be there. Again, electrical characteristics which we can choose based on the my timing constraints, my delay my power constraint. Based on that I have to choose. Okay, and even I can predict that how much it is going to be, how much power it consumes, how much delay it consumes, we can predict by using AML technique. So typically we are using AML for automation, for optimization, and for predicting the performance metrics of the circuit parameters. So again, predicting the performance of the layout before the actual running simulation. So that's something what we are going to do. This is a example for this. So now let's say that what is the key challenges that we are facing in the a traditional VLSI design flow. So that's something which we'll see here. If you look at traditional design VLSI design flows, it take long design cycles. Again, for every process, every process of the VLSI design flow, I have to do multiple iterations. Again, specification to RTL, I have to do at least one or two multiple iterations. What are the things I have specified? I have given as specifications, and whether it matches or not, I have to verify it. And RTL to gate level, again I have to do this one. So it takes longer design cycles. And again, another important issue challenge is difficulty in manual optimization. Again, we use some kind of algorithms, and all these algorithms are meta heuristic algorithms. That is something like a simulated annealing. This kind of algorithms are something what we use it in the these tools, whatever the optimization tools that we are using here. Okay, and because our objective here is to find out the global maximum and global minimum. So that's something what it will be there. So for that reason, we use all meta heuristic algorithms. And we need to do this one, whatever the designs we are implementing, it has to go for a multiple iterations. Okay, to meet the timing, to meet the area, and to meet the power. Okay, so it has to go for multiple iterations for every time we design it. Okay, and so again, whatever we got it in the last iteration, we may not get it in the next iteration. That's something what typically happens when you go for a this approach. Okay, uh, so again, it another is, important challenge here is hard to detect the bugs in the early in the design flow. Again, is there any errors in the design? It is very difficult to detect. Okay, the way we model that's something what it goes here. So this is another biggest challenge. Again, the errors here, whatever I am saying, bugs, in the sense somewhere, if I keep this kind of component, so the over thickness of the my metal layer, or let's say over thickness of the my VDD line or ground line. So these are all shortage of two VDD lines. Okay, or short of one signal with the VDD line. These are all very difficult to detect in the traditional VLSI design tools. Again, now I'll also bring the context of ML. Since let's say that I have a ML model where I have used X standard cell and Y standard cell in combination on a same X some small size of area, so where it lead to some kind of uh, after fabrication we come to know that it lead to a some kind of short in the chip. Okay, that's something what we got it. That is the data that I am having. So that is the historical data. That's something I will consider when I consider to the when I come to the my new model. That's a AML model based VLSI design. Okay, so this is because I don't have any historical data in the traditional approaches, and it's very difficult to detect the bugs here. That's something what the designer experience only. Based on that only he has to do this designing. Okay, so these are the challenges that something what the traditional design flow has. So now I will little more introduction about machine learning models. That's something I will give here. Again, machine learning will have we can view as a three different approaches. So one is going to be a supervised machine learning model. Okay, in this we'll have a labeled data, and so that is labeled data will be available here. and that's something what I am using. Example, if I take a standard cell, for that standard cell, what is the power it is going to consume, that something will be there, because essentially VLSI design, so when you talk about semi-custom VLSI design flow, we'll have a standard cells will be there, again for a specific library component, and for each component what is the power value, what is the delay it takes, and those are all will be there. And apart from that also we can have a one standard cell and another standard cell in combination, that gives the one logic function, then what is the power value, what is the area, what is the delay, these are all will be there with respect to the standard cell, which is going to be a labeled data, we call it. Okay, and that's something what we use in case of supervised learning model. And the other one is unsupervised learning model point of view. So where we typically use means we'll identify some kind of patterns in a unlabeled data. Again, let's say that some kind of adder design I'm doing with respect to the ripple carry adder, and so when you talk about ripple carry adder, where I will be cascading a some kind of standard cells in a cascaded fashion, which lead to a larger delays. That's something what we have. So this is something what when you cluster and see that we will get some kind of property. Okay, so this is something what we call it as a unsupervised learning models, or we call it. Okay, and then we have another approach of machine learning is something, the third branch of machine learning implementation. So we call it as a reinforcement learning. This is something is a very interesting approach where we'll take that reward as a one of the metric, and based on the reward we'll take the actions. Okay, so this is something is very useful in the majority of the cases. So I will if I take this action, what is the reward? If I take this one, what is the reward? Okay, if I use this cells in combination, and then what will be the delay, what is the power, that's something what my reinforcement learning will provide me, such that it will be very useful in the design context. Example for this reinforcement learning is a self-driving car learns to navigate using RL by minimizing the reward, like staying on the road, or that is something is the reward point which will be considered. Is there some questions up to this point? Let me check. Yeah, if you have any questions, you can type in the chat box. I'm happy to answer that. Okay, no questions. So now let's understand that again, if you look at this AI/ML models, ML models are most commonly used for VLSI design flows. The reason is it works with the historical data, and even here also we need a historical data such that I can get benefited because of the old designs. Again, old designs, and let's say 45 nanometer with a certain combinations, what is the error got it, and let's say the same thing if I use it in the 32 nanometer, what might be the thing I can get. I can predict those things I can predict it. So in this case, so now let's understand that how this ML model works, and so we'll have a data. So it means where we are extracting the RTL features of that something is one of the example is given, or let's say that I have a standard cell where every standard cell attributed with some kind of area, power, delay mechanisms, or combination of standard cells, or function, or a mega cell, or micro cell. These are all the means a combination of standard cells which will form as a mega cell, micro cell. In that case, so what is the parameters? That's something which will be considering here. And then once we collect the data, will be pre-processing. So it means we'll be cleaning and formatting the data here, and then we'll extract the required features, something like what is the area I want, what is the cell count, and or I will estimate the what is the power it consumes, summation of all the things, or what is the delay. So what is the longest path in the circuit from input to output I will take when by considering the graph, and then I will estimate the delay in this case. Okay, this is how I will extract the feature, and then I will also model the training using any kind of decision, any kind of algorithms, that's machine learning algorithm. Most popularly, we will use like a decision tree algorithms. Okay, is the one of the commonly used machine learning model. And then once we build this, once we do this model training, then we'll go for a evaluation where we'll check the prediction accuracy. So that's something what I'll be doing in case of ML workflow. And so once it is done, it meets my requirement, then I'm going to deploy it. That means I'm integrate the model to in the design tool such that it gives the optimized design for me. So that's something what we are doing. Okay, so this is the key steps involved in any of the, this is the key steps involved in any machine learning workflow. So we need to have a data collection and data processing and feature extraction, and then we'll have a model training, and then we'll do the evaluation. Finally, we do the deployment. Yes. Now let's see that I'll also quickly go through the some of the ML algorithms, because you're all electronics related people are there. So I'll quickly go through it, some of the ML algorithms. So commonly used machine learning algorithms are one is support vector machine. Typically we'll use this one for classification purpose. So we can classify the data into a different categories. For that reason we'll use this support vector machine. And then we'll use the decision trees such that we can easily interpret the model, and we can understand what exactly it is going to be done. So decision trees is the another one. And another one is artificial neural net, where we can detect some kind of patterns in the designs whatever we have, okay, or whatever the clusters we have considered. And then even convolution neural networks, which is the most commonly used algorithm. Typically, when you talk about when you want to handle the spatial data, in that case, it is going to be very useful. Okay, and even graphical neural network is another one which one can also use. This is also very useful for netlist and connectivity based design point of view. This is going to be very useful, because you know that our VLSI circuits is a bipartite circuit. Again, I have an input and I have an output. From input to output, my signal flows. That's the reason why we call it as a my digital circuit, whatever we are using. So we call it as a bipartite graph, we call it. Okay, and when you have a bipartite graph, and analyzing the bipartite graph by using GNN is going to be very easy. So these are the some of the algorithms that typically we use it. And now coming to the some of the tools that we use, and some of the libraries that uses is for machine learning point of view. So we use TensorFlow or PyTorch typically for deep learning point of view, and to extract the features we'll use deep learning. Let's say that I have a 45 nanometer based standard cell. The same thing I have modeled in a 22 nanometer or 32 nanometer. In that case, what will be the features of that one? That's something I can predict from the historical data that I have. So that's something what I can do by using this TensorFlow or deep learning. And scikit-learn, this is a classical machine learning model. And this another one is Keras. This is a high-level wrapper for deep learning. These are the some of the tools and libraries that typically we use. Okay, and yeah. Now we understood what is the what is it, what is machine learning, and what are the types of machine learning, and what is the machine learning workflow also we understood. And then we also seen about uh, what are the algorithms that typically uses in the machine learning point. Okay, so now till this point, if you have any questions, please feel free to ask questions. So yes, there is a question. whether AI/ML concepts are included along with the existing VLSI EDA tools. See, if you look at today, majority of the VLSI industry, they are implementing, means they are using this AI/ML models in their tools. Okay, if you look into that, all the things. But again, when you talk about tools point of view, they are already using this one, and but when you talk about standard cells and the prediction error point of view, bugs point of view, that data, it is mostly kept as a proprietary, and they are not sharing with anybody, because if they share, their market leadership will go off. So that's something what they are doing that. So this is something is one of the biggest challenges. We don't have any historical data in the historical data when you talk about this VLSI design flow. It means I have a standards. I have a circuit where I have a circuit which will take 100 full adders. So then the same, I have another circuit where there are 200 full adders. Then what is the area power delay? Okay, so these are all some things. Openly, we don't have any data. That's something is the biggest problem here. If you want to really optimize it, okay. But if you talk about tools point of view, they are already using, because even the tool is also is optimization techniques only we are doing. So they are using certain level of optimization which is generalized in nature. Okay. Yes. Is it clear? Okay. Yeah. Any other questions from others? Yeah. If you have any questions, you can ask me such that I can clarify, and then I can move on to the next how we'll use this one. So we'll see. Fine. Yeah, you can type in the chat box, or you can unmute and also and ask. So now let's go on. Let's move on. So now, if you look at what are the metrics that typically we consider in the evaluation, one is again, when you talk about machine learning models point of view, so we'll consider that accuracy. It means the correct prediction. That's something divided by the total number of prediction, that we call it as a accuracy. I'm talking here, the metrics is related to machine learning model. How good my machine learning model? So that is defined by in terms of accuracy. So that is correct prediction divided by total prediction. And then we also have, there is something called precision recall. So this is very useful to understand that how good my data is there, the data behavior, and is there imbalanced data is there or balanced data is there. That's something what we can understand by using a precision and recall mechanism. And we also have a confusion matrix that shows that true positives, true negatives, false positives, and false negatives. That's something what it indicates the confusion matrix. And then we also have a loss function that indicate the prediction errors, like mean square error, those things, even cross entropy. These are all some things which we can compute as a loss function. Again, these are all the how good my model. See, this is again, when you talk about VLSI design case, we are only concerned about area, power, delay, and as I mentioned, one of the key metric is power delay product, or energy per operation. That's something what we are only concerned. But which model will deliver those things? Okay, so that model is how good it is. So that also we have to consider here, whether the model has a properly done accurately, how accurately it has been predicted. So those things also we can evaluate. So because these are all the learning models, machine learning models, so we need to have a mechanism to analyze that how good my model is. So for that reason only we need this one. Okay. So these are the metric. These are machine learning model metrics. Okay. Uh, that is accuracy, precision, recall, confusion matrix, and loss function. But if you look at chip designing point of view, energy per operation, power, and delay and area is the three key things which we consider. Are there any questions? No. Fine. So now let's move on to the. Now I'll talk about how we are going to use AML in the VLSI design flow. I'll give one case study, and I will also explain such that you can understand little detailedly. So one is in the design phase. So one is front end design, where RTL design and functional verifications. This is the place where I can use it. Okay, and when you talk about middle end, where we have a synthesis and floor planning point of view, I can use my AML techniques. Even in the placement and routing and sign off point of view, so we'll be using this AML approaches. Okay. Typically, we call it as a VLSI design flow. Front end, back end is the thing, and these are the operations that typically we do here. So, with respect to that, each operation that we are doing here. So today, if you look at again functional verification, majorly they are using chat GPTs and other things to verify the designs. Okay, and this says that when compared to the assertion based engines or the other models, that traditional approaches when compared to this function the functional verification by using chat GPT and other things are more efficient, and it is very easy to do it. Okay, and you can see that there are a lot of research articles that they're also publishing with respect to that. You can also verify it. Okay, and as I told that these are all the different places, places in the real estate design flow, and where we'll have a labeled data. If you are having a labeled data, and definitely you can you can apply the ML, and such that you can reduce the time, and you can improve the quality of your design. So now let's talk about front end point of view, AI front end point of view. So we can predict the quality of result early itself. So based on my design, so that's the one thing what I can do here. Example is use a regression to predict that if RTL will meet my timing after synthesis. Again, before synthesis itself, I can estimate that this RTL layout, RTL model, whatever I got it, that's a register transfer model that I have in my hand, in my design. By using a regression approach, I can predict that whether it will meet my timing constraint that is being set. So timing constraint means, let's say that I'm designing a processor. When I'm designing a processor, assume that my processor should have a clock width is going to be a 1 by 3.8 gigahertz. Okay, so that's something what we are keeping, because I want to design a processor which is going to have at least 3.8 gigahertz frequency. Okay, again, below that I don't want. I want higher than that. That's something is greater than 3.8. That's something I want to meet it. Okay, so that's a timing constraint that we keep it here, and that one itself we can predict it in its RTL model itself. Again, how we can predict is because each component that is there in the RTL model, it is also labeled, and by using the labeled data, and by using the regression, one can compute, and we can tell that whether it will meet the timing constraint or not. So what is the benefit here? If I use this one is I can do faster iterations. Fastly I can design my RTL, and I can reduce the last stage surprises. Again, any errors that is coming in the final stage, that all I can reduce it. That's one of the advantage of going for this approach. So the next one is the other thing is machine learning for RTL power estimation. So essentially, if you look at this traditional power estimation models, it is going to be a simulation heavy model, and we typically use Markov process based simulation. That's something what we are using, and even you can see that there are different models which we can consider, and where we can estimate the power, which is given in the chapter 4 of Neil Westay textbook. You can read that. There is a power chapter, And again, he detailedly describes in that book what is the drawbacks of that one. Okay, each model also. Okay, so again, you know that Markov model is a simulation heavy. It will take a lot of simulations to get the results. Okay, and my ML models can instead of traditional models, if I use the ML model, it can estimate the power from the RTL code feature itself. Again, because we have a labeled RTL things are there, so from that I can estimate the power also in the RTL model itself. Okay, so that's the one of the advantage here. I can train the model using a switching activity. That's something alpha factor, because I can see that I can choose the components also such a way that it will have a lesser activity factor. This is something is the greatest feature that we can use here, and even fan outs and other things also I can minimize it based on my design requirement and power constraints point of view, and signal counts and logic depth also I can estimate it at this level itself. And we can estimate here the output is we can estimate that instantaneous power estimation we can do again in milliseconds we can compute it, because I have all the label data of because I have a RTL model and combination of RTL components and which are all labeled already. So those data from that I will extract it, and then I will compute the delays. I will compute the power. Okay, so that's the reason why it is very fast. I no need to spend much time, and that's the thing. In milliseconds, I will get the result. So that's the one of the key advantage here. So the other advantage is a we can use for functional verification. So what is functional verification? Let me explain. And again, whatever the design I have done, so where I am going to feed all the combinations, all the possible combinations. Again, what are the possible combinations that user can feed? So those things I will feed it here, and I will verify its behavior. So that's something what I will do in case of functional verification. Again, if you look at what are the things we are doing in the lab, that where we call it as a informal verification. Exactly what we do in the informal verification is, let's say I have a circuit where I have a n input, and and then I have a k output. So where I will feed the 2 to the power of n combinations of the test vectors, and then I will see that what are the things I will get it. That's something what we do in case of informal verification. But when you talk about formal verification, I'll give all the possible combinations. That's something what I will do here. So such that I can identify the test coverage gaps here. So that's something what we'll do in case of functional verification. So again, if you look at majority of the jobs today are they're all there in the functional verification front only. Okay, and we can generate the high value test cases by using machine learning here. Okay, again, this is one of the advantage here. Example is we can use reinforcement learning such that we can guide the test generation that target the hard to reach hard to reach states also. So that is the one of the advantage of using a for functional verification. Again, if you look at functional verification point of view, there are many articles today you can see in this domain which where they have applied more A and ML techniques to optimize it. So similarly, I can also predict bugs at the RTL design itself. So again, as I mentioned, this one earlier I also explained. We can analyze the commit history and design complexity. That's something what in my hand in the design itself is there, and where my ML models can predict these modules, which are the modules that like to have bugs. It means what are the combination of cells, what standard cells that may lead to some kind of stuck at zeros or stuck at one, or any kind of other faults. So we can predict in the early stages itself. So that's the one of the advantage here. But for that we need to have a accurate, realistic data set. That's something is very necessary. And again, today these data sets are all highly proprietary to the specific organizations. They won't share it until unless if they only give the efficient design, but they will not share this data. Okay. So even the tools that they use is random forest or XGBoost. For high accuracy, we can use in the bug prediction point of view. Okay, so next we'll talk about how we can use AI in the logic synthesis. That's a high level synthesis point of view. So what exactly we do is we will have a automate directives that tuning that circuit. Somewhere we'll do loop unrolling, we'll do somewhere we pipelining. Again, when you are doing how many levels of loop unrolling I have to do in the hardware, such that it can meet my timing constraints. Okay, that is from the folded design to a unrolled design. That's something what we can analyze here. And even sometimes where if my timings are not matching, where I want to do the pipelining, even which are the components I can group together such that they will have a approximate equal delays. That's something what each group that I am having, such that I can insert the defib class between one group to other group, such that I can perform the pipelining. These are all some things which my AI model can help me in analyzing this one. So in this case, AI models will learn from the previous high-level synthesis runs that we have done it. Again, for every design, whatever we have, so how it has behaved, all the recorded data should be there, and that's the historical data which we use to feed to the current running design, such that I can predict these things also. So the example here is what exactly we do in case of synthesis is we will optimize the delay. That's a delay by selecting the correct unrolled factors. Let's say that I have to make it my circuit which is going to have 20 iterations. Let's say I unroll that one to a five iterations. That is going to be a very good. So that's something what my ML model instruct me by analyzing from the historical data, and that's something what I can adapt it, and I can unroll it, and I can synthesize it, and then I can estimate the my circuit parameters. On the same lines, I can also do the placement point of view. I can predict that placement related with convolution neural network. I can do it. So where CNN learns the spatial patterns of the cells placement, and even layout density map it can construct, and even it will have a netlist info, and from that we can predict the cell placement such that I can minimize the congestion. So this is the one of the most complex tasks in the any traditional design VLSI design flow, because you know that the placement is something every placement is going to be a one solution. This is something like I want to construct a 2 BHK house, and let's say that I have a bedroom is going to be a 10 by 10, that is going to be a 2 size, and I have a kitchen which is going to be a 10 by 8. Assume that again like that I have a layout, and living room will have some layout, and toilets. So now what are the possible combinations I can mix and keep it? So every possible combination is a one solution, but which is the optimized one? Again, optimized one is something like when you talk about 2 BHK house, so which is going to have a quickly access from one room to other room, and where we have a good ventilation. On top of it, we have a good vastu. So put together, that's something what we call it as a optimized design. Okay. So when you look into the traditional approaches, we use simulated annealing approaches or any other meta heuristic algorithms that we use it. And again, these meta heuristic algorithms also it has to run for a multiple iterations, and it is slowly converged to the optimal solution. So that's the one of the drawback here, and which now by using my CNN algorithms here, we can fastly converge and we can do the efficient placement. Okay, so there is a tool called Dream Place. This is an open source and GPU accelerator placer, which we can use it and where it do the efficient placement. So similarly, I can also route the prediction by using reinforcement learning. Okay. Again, as you know that reinforcement learning is a step-by-step where we'll have a reward and action. Based on the reward, I will be considering, I will be doing the action. That's a ML model. That's something it works here, and it treats the routing as a game, and where agent earns the reward for legal and efficient paths that I'm having. So RL models learns to route the wires, because one of the when you talk about routing, the overall route means overall wire length I have to minimize it. We also call it as a half perimeter wire length. We call it. We want to reduce the overall wire lengths. Okay, such that I can minimize the congestion, and even I have to consider that timing violations also. So this I can do very efficiently with the help of RL models. Yes. Any questions up to this point? Yeah. Do you have any questions? So please feel free to type the questions. I'm happy to answer that. So next one is clock tree synthesis optimization. Typically, we also use in the designs clock tree, and because my clock will be supplied to the different components in the my chip, so we'll use the clock tree, and even my ML model predicts that optimal buffer and inverter positions when I'm using a clock tree, and it helps to achieve low skew and minimal power. So that's something what we can do in this approach. And another thing is another important aspect is my power performance, power and area prediction I can do here. So it means I can predict the power, performance and area outcomes also at every level I can do by using my ML techniques. And similarly, we can predict whether a new floor plan meets the frequency goals or not. So this are also we can verify from RTL level, and similarly gate level or my switch level. That's something what transistor level or even at the layout level, I can analyze this one, I can get these parameters. So another advantage is I can also do the yield prediction. So yield prediction means if I manufacture number of chips among the 100 chips, how many good chips are the things we call it as a yield. Okay, so rest of the bad chips which I will be putting into the dustbin. So again, why means because these are all there are 20 to 30 chemical processes are involved, and where we need a very precise currents and voltages and laser based etching mechanisms. Somewhere a slight variation in the frequency, voltage and current that may lead to some kind of short circuit in the wires that are passing inside the chip or component. That's something what it will happen. So these are all which we need to predict. We can predict it before manufacturing. Again, use the past manufacturing data. Again, what are the things that is happened when you run the array multiplier and with this kind of setup, or when I run the same array multiplier with a different gap sizes in the standard cells. So these are all analysis historical data from the earlier manufacture. That's something which I will collect it, and those data which I will use, and I will predict the chances of defect under the variation. So that's something which I am going to do. I can predict that I can improve the yield. Again, I can improve the good chips by making that by placing the component distance initially itself such a way that it will not do the short circuit, or no stuck at fault, or stuck at 0, stuck at 1 will not happen. So those something which I can do here, and even it help us to decide designs need a more broadband. So these are all some things which we can do in the early stages itself. So next, again, when you look into the chip, so we have a n input, we have a n outputs, will k outputs will be there, and again, if you consider the chip which is going to have a, for example, more than 50 inputs, then 2 to the power of 50 combinations I have to feed in order to exhaustively test the chip, such that my chip is going to be correctly works or not. Again, whatever the output that I get after the fabrication, that has to be matched with the my simulation output. We call it as a golden response. So such that my fabricated chip will have the same functionality that has been modeled in the RTL, that has been that has been fabricated. Okay, so that's something which we need to confirm. For that reason, we will go for a testing. And when you talk about testing, and when you have a number of input combinations is greater than a certain number, it is going to be impractical to test, because if you talk about 2 to the power of 50 or 2 to the power of 60 combinations, or it is impractical to feed this many test vectors, which we need a super high powerful computers which can do this one. Okay, in order to reduce the this computational task, again we are going for a design for testability. Again, what exactly we are doing, when we are designing the circuit, in the circuit itself we'll also put the testable circuit, such that I can feed the test vectors and I can get the responses, I can verify it. Again, I don't need to test all the exhaustive 2 to the power of n combinations, which what exactly I'm doing is I'm using there is something concept called reducibility, where I'm reducing the 2 to the power of n combinations into a 2 to the power of k combinations, which is of few hundreds or few thousand combinations will be there, and those things only I'm going to feed to the my chip in the during the physical testing phase after the fabrication. So that's something what we call it as a DST circuit, DFT circuit insertion in the design phase itself. And even this DST scan chain, which is typically inserted into the my design, and which are the places I have to insert, and such that I can I can reduce the number of test vectors, and I can do the full fault coverages, 100% fault coverages, how I can cover or not. Those things I can analyze it by using the ML models. So ML models finds best locations for test logics to maximize the fault coverages. So that's something what we can do in this scenario. Yes, any questions on this DFT optimization? And this is another area where majority of the people are working today. And again, one of the biggest challenge when you talk about academic setup is we don't have any data sets for all these things. Okay, that's the one of the challenge, and all these things are with the either fab people or with the design houses, not with the academia. So that's the reason why the research, VLSA research in these domains has been thinned a lot from the past, again, we can say a couple of years. Okay, because we don't have any historical data to use that, and to do this one. Otherwise, we can see that very good papers that might have come. Again, today we as designers, they just use some kind of synthetic data, and based on that only we are doing this one. Again, what is a good, whatever the synthetic data we are using, how good it is, and whether it has a balance or not, these are all very challenging to predict it. Or how close to the accurate designs also very challenging. So similarly, we can also do the formal verification bottlenecks, where we can use ML to predict which assertions to take, that takes longest to prove. We can do this one, and even we can prioritize the resources according to the my assertions that I'm having. So this is another place where we can apply. And even intelligent test case generation, again we can generate the models that to create a stimulus automatically by using ML models. We can do it here. Even we can guide the generations based on the convergence feedback. We can also perform this one. And even we can do that auto ML for architecture search. Again, which is the best architecture I can use it, that also I can perform here. So auto ML optimizes the neural network architecture parameters, which we can use it here. Apply some concept to optimize the microarchitecture of the chip. Let's say that there is a adder. Which adder is going to be a best one? Let's say that can I use ripple carry adder, or can I use Coxstone adder, or can I use prefix adder, or I can use some other type of adder. So those choice of adder also I can do with the help of ML techniques. Okay, even multiplier context also the same. Okay, again when you talk about mega blocks, micro blocks, or whatever the mega blocks, micro block, functional blocks are there. In such cases, which block is going to be the right one, I can decide by using this auto ML optimization approaches. So there are tools that like Auto ML, Google's Auto ML, that is used for TPU architecture design. Again, here what exactly we are doing is we are using a, when you talk about TPU architecture, again it's a matrix multiplication hardware. Okay, so that design we can develop this models we can build by using Auto ML models that is developed by the Google. So now I will quickly go through some of the case studies. There are some of the CNN based placer is available, and which will achieve whatever the quality of metrics that is provided by the commercial circuit tools. The same thing we can also use by using Google Dream Place, and where it runs 10 times faster, 10 times faster on the GPU. Again, this is the most powerful tool where I can quickly get the results. Essentially, if you look at this design phase, it takes 4 to 5 days like that. But when I'm using this one, I can quickly place it fastly. I can get the results. I can estimate the results. And even when you talk about architecture point of view, ResNet Plus, which we can use ResNet along with the density map inputs, which we can consider for architectural optimization point of view. And when you talk about NVIDIA, again another case study where NVIDIA deep learning floor planning, so where it uses the graphical neural network for block placement. So it uses a graphical neural network for block placement, and where it learns the timing, congestion, and floor planning quality. We can measure by using this NVIDIA deep learning floor planning, and which will achieve faster convergence, and where it will go only fewer steps, only fewer iterations only, such that we can get it. And similarly, we have when you talk about analog layout generation with GANs, is another case study which we are doing by using these are some of the examples where we are using machine learning, AI, deep learning models to design the circuits. Okay, so where we are using a generative adversarial network to produce layout images, we are using this one, and where it learns the symmetry and matching, and that's impedance matching and circuit parameters related estimations, and even DRC rule estimations we can do here. And some of the tools like InstaGAN and LayoutGAN, these are all some things which we can use it, and where we can generate the analog layouts by using this generative adversarial neural networks pointer. So these are the list of AI, ML, and deep learning reinforcement learning techniques that we are using in the various stages of VLSI design flow, and even in the design point of view. I have presented some of the things. So now what exactly I will do is I will just give that what are the tools, frameworks and data sets that are available for the researcher to use. So those things I will quickly present here. So if you look at ML enabled commercial tools, one is Cadence Cerebrus. So this is a AI driven digital implementation we can do. There's a Cadence tool we have, and similarly Synopsys DSO dot AI, which is going to which uses the AI for design space optimization. We'll use this one, and Siemens Solido, where this tool we are using for unlock verification and variation modeling. We can perform by using AI techniques. And coming to the public data set, so we have for placement and routing point of view, we have ISPD benchmarks. This is something what we are, it is available. And when you talk about Open Road, it's a open source software tool where I can design the VLSI design flow from RTL to ZDS to flow. So that's something what we can do. We can use from the Open Road, and we also have CircuitNet, which will provide the data for ML training in the EDA. So this is a circuit net we can use. That something is available here. And yeah, this is some of the data sets, something what you people might be looking. Again, we don't have all the types of data sets. That's something what we have seen in the design flow. Again, somebody has to create it as a students or some academic people has to create the data set for every stage. Once it is done, then only we can effectively use it, and then only we can demonstrate these approaches to our students in the academic environment. Okay, that's the biggest challenge here, because right now all the data sets are proprietary and they will not share to anybody. Again, my recommendation is if you are on to do this generation, you can start with the whatever the MCNC benchmarks or whatever the ISCAS benchmarks circuits are there. Those are all the things which you can do. Somewhere you generate the data set with respect to the RTL models. Somewhere you generate the gate level models, gate level netlist related, and we can do the analysis. Again, we have to do for each library. Again, library in the sense 90 nanometer, 45 nanometer, 32 nanometer, like that you can do it, and such that you can keep this one. And similarly, placement point of view, routing point of view. These are all which we need to do. Then only once it is available, then only academia can use it. So as of now, we can learn the concepts, but we cannot apply. That's a biggest challenge here, because we don't have a realistic data set, a standardized data set for every phases of the VLSI design flow. That something is not available as of now. Okay, so OpenFlow that uses from RTL to ZDS2, but it's also it's an open source course. You have to detailedly understand each level, how they are doing all this thing. Then you can implement it. So now we'll talk about some of the open source framework that is available for chip designing. So DMPlace, that is GPU based placement, is something is an open source which we can use it. And Auto TVM that tune the compute kernels for efficiency. This is another framework. It is available. Again, OpenRoad is one of the very good tool which we have used it, and we have fabricated a 4 chips. We got a physical chips from the Google Fab where they have given, they have shipped it to us, and again we have submitted 38 chips by using OpenRaid. So full EDA flow we can do here, and from RTL to GDS to generation. It's a very simplified, very easy approach which we can do it, and that's something what we have done it, and where we have fabricated. And yeah, as I mentioned, data labeling in VLSI. So few labeled data sets only available. That something is out there, and we don't have for every stages of the VLSI design flow. We don't have a labeled data set. That's one of the biggest challenge here. And yeah, we can use semi-automatic labeling and simulation, which somebody has to do and generate it, and label the netlist for paths also, such that I can estimate the timing criticals, non-critical timing also I can estimate it here. These are the some of the challenges that is there with respect to the data set. In fact, we also initially started generating the data set. Again, there is a one company has approached us to do that one, and even they asked us to estimate that if my circuit has this many number of gates, then how much time it will take to convert into a what is the number of process I need it, what is the memory I need it. They also asked us to estimate it. We have done certain level of work, but it is not of we have done some initial preliminary work. We generated some kind of data set, but we need to do more with respect to that. So similarly, research trends and challenges in this domain. So need for a standard data set is the big question mark here, and lack of public and automated data sets slows the progress. Again, entire academia is just eagerly waiting who will post this one. That's one of the pathetic situation in this domain. And synthetic data may not generalize the entire design flow. We can use synthetic data. We can design and we can write the papers and all the things, but it won't capture the real scenarios. Okay, so that's the biggest challenge here. And similarly, explainability and interoperability. Designs prefers the explainable decisions, and black box models hinder the adaptation. And some of the tools like Sharp and Lime for model explanations we can use here. So that's a thing. And other generalized limitations is models can be trained on 28 nanometers, but the same models whatever I have trained for 28 nanometer will not work for 7 nanometer. Again, for 7 nanometer I need to create a, for every stages of the VLSI design flow I need to create a test this data, historical data. Again, I have to do a lot of things. Means the way I have done it, the same approach I have to do for this one also. So this is one of the challenge here. And retaining means restraining is costly and time consuming here. So that's another issue here. And coming to the integration challenges, legacy EDA tools are very rigid. Again, today if you look at, we are not using legacy EDA tools, and need a flexible APIs and ML aware interfaces. That's something what we need to integrate with this older EDA tools, such that we can design efficient chips by using ML approaches. And coming to the cost of training of a models, so deep models require GPUs and long running times. And again, the trade-off is also accuracy versus compute cost. So this is also we have to consider when you are designing. So now coming to the future directions, AI on chip versus AI for chip. So AI on chip means that runs AI models on the chip. That is something what chip that runs the AI. For example, tensor processing unit or neuromorphic processing unit. Okay, network. So that is something what we called as a AI models on the chip. Okay, and AI for chip means AI is used for designing the chip. So that is something what AI for chips. Okay, and AI can help designing the better AI chips, even the TPUs and NPUs, neuromorphic processing unit. These are all I can enhance it. And again, you know that today, if you talk about your smartphones, also has some kind of neuromorphic units, and TPUs are all available as a co-processor. Again, as you know that Intel also they are rolling out in the future. Right now, you have a 4-core processor where 4 homogeneous processors are available. In future, we will not have like that, where we have a processor core, and then we have a TPU core, and then we have a GPU, and then we'll also have a neuromorphic unit also will present. So that's something what the processor structure also comes in the down the 3 to 4 years we'll have. Okay, so again, when it comes to the core design trend, yeah, simultaneous optimization of hardware and ML models, that something is necessary. and ML assisted hardware acceleration definitely help, and even quantum ML in VLSI also we can use, where early research using quantum algorithms for optimizations we can use it. Again, when you are using a quantum circuits also, again quantum computers, again ultimately my quantum computers has to interact with the electronics. Okay, it means we need a circuits also. Again, especially when you talk about control readout circuits, we need to build it. Whatever the circuits right now we are using, we need even because quantum computing works very fast, right? So we need a electronic circuits that will operate at that level. In that case, I need to build chips at very lower nanometer technology, like 7 nanometer technology, something like that, which will have a lesser delays, which can meet the my quantum computing related requirement. So that's something what we need to do in this case. Yeah. In summary, I'll just summarize this in 2 minutes. So AML transform all the stages of design, chip design flow. Definitely, it's very useful. Again, unfortunately for academia, we don't have a data sets to use this one. So we can do faster design, better power, area, delay optimizations we can do, and this leads to a lesser number of bugs in the design. So that is the benefits, and tools and data sets also need to matured in this domain. So this is the, and similarly from RTL power estimation to the post layer optimizations, we can perform by using ML models, and yeah, even real world examples show the significant speed up when you are using ML models. These are the list of references. That's something which I have used for this presentation. And if you have any questions, you can ask me. I'm happy to answer that. So I'm done with my presentation. If you have any questions, you can ask me. Yeah, we are on time. We have another 6 minutes. You can ask me the questions related to whatever we have covered.
Any questions from the participants?
Good evening, sir. Can you listen me?
Yeah, good evening. Yeah, tell me.
Sir, there's a cadence tool. We have so many parts. In which cadence tool we have this A and ML operations, sir?
See, the point is, I don't know which tool you are. I have told one tool where it has a AML integration. So I'll share the presentation also. You can go through it. Okay. But actually, right now, whatever they are giving for academia free of thing, there is certain level of AML only they have put it. Okay, they have integrated, especially when you talk about this optimization. Which are the places we need optimization? Okay. The name of this one is let me uh, uh, recollect what is the tool name is. Yeah, but if you look at open road, they have implement, they have everything is done in that. Okay.
Thank you, sir.
Yeah, Cadence Cerebrus. So this is a tool where AI-driven digital implementation. Again, this tool is for digital design only. Okay, digital chip manufacturing point of view, RTL to ZDS to for digital design we can use. Okay, fine. Any other questions? Fine. If there is no questions, yeah, yes, madam.
Yes, sir. I think we can conclude the session, sir.
Yeah, if there is no
Yes.
question, then we'll end the session. Thank you for your patient listening. I hope you understood some concepts. Thank you.
Yes. Yes, sir. Thank you, sir. Thank you, sir, for such a wonderful session. I'm sure all of us have gained some valuable knowledge and new perspectives. Thank you, sir.
Thank you all. I'm leaving. Huh? Okay.
Yes, sir. Thank you. Dear participants, I think we have posted the tomorrow's schedule in the WhatsApp group. Once again, I'll intimate tomorrow's sessions will start from 2 p.m., not from the 6 p.m. Schedule. So we will be having three sessions: 2 to 3:30, 3:30 to 5, and 5 to 6:30. So after the completion of three sessions, you will be giving a feedback in the ATAL portal. Once you give the feedback in the ATAL portal, you will be giving a test from 6:30 to 7:30. After the completion of the test, we'll be having a valedictory session. So this is the tomorrow's schedule, and we look forward to your enthusiastic participation tomorrow, as we are going to bring this FDP to a memorable conclusion. Thank you. And the feedback link for the today is posted in the WhatsApp group. Thank you.
Madam, how many questions, madam?
Sir, I think you will come to know by tomorrow, sir. And participants, again, one more thing, gaining 70% of the marks is mandatory for the generation of ATAL certificate.